So we've talked about forces. We're pretty familiar with forces. Let's move on to fields. Okay? This is a little bit more subtle. A force, you feel. A field, you also kind of feel, but it's like more fuzzy. All right? So the Newtonian description, because Newton was pretty smart, but he didn't know everything. A exerts a force on B. If we draw the force of A on B, it's just this nice vector. Okay, whatever. The field description is a little bit different. You get the same result, but it's a different way of thinking about it, sort of. I hesitate to say philosophically, but yes, philosophically. Okay? The field description says A creates a field everywhere in space, regardless of whether or not there's B. Okay? Now, it's like kind of potato, but mathematically it's not. All right? What this says is, think of it as a gravitational field, right? If you're not here, is there still gravity here?
Yes.
Yeah, what does it come from?
The Earth.
The Earth. So as long as the Earth is here, there is a gravitational field everywhere around the Earth. Okay? You're incidental, right? We can put you at a particular point in the field, and you'll behave a certain way depending on what the gravitational field is at that point. All right? The end result is the same, right? The gravitational field times your mass gives you the gravitational force. Okay? The same with the electric field. So if you have a positive charge, there's an electric field around that positive charge. The electric field points in the direction that a positive charge would travel if it were placed in that field. So for instance, if you put another positive charge next to that positive charge, what does it do? It repels. Okay, and if it's free to move, it's going to move away from the positive charge. Okay, so it's behaving, it's reacting to the field, which is a little subtle difference from a force, right? A force requires two charges. A field only requires one. So you put a charge in space and it creates a field. You put another charge in space and it interacts with the field. Okay? Which is different than saying any two charges have these forces. That's really limiting. It only tells you what's happening at one place. A field gives you a map of what's happening everywhere due to that one thing. So like, for instance, from the Earth, if we know there's a big mass here, we know everywhere around the Earth there's gravity. There is a gravitational field. So if we put masses around the Earth, we can predict how they're going to behave based on that field. Okay? We don't have to calculate the force individually for anything we would put in the field. All right? So that's the difference. And so the way we would think about this is we'll say, even once we calculate the field, we don't even care that A's there. Now there's just a map of what's going to happen everywhere in space. So when you put B in the field, you say B behaves this way because it's interacting with this electric field. Okay? Like, once you know the acceleration due to gravity, do you need to know the mass of the Earth? No, right? Once we know how Earth interacts with the space around it, we don't need to know all the specific specs of the Earth. We know how things are going to behave without specifically knowing the mass of the Earth. Okay? So, just as a sort of fun experiment, somewhere on this screen is a hidden charge. Okay? So let's say we put a positive charge here, and we see that it experiences a force this way. What possible charges could there be, and where might they be? Let's say there's a positive charge on the screen.
Right.
Yeah, it would be here. We know, just because of the behavior of this charge, that there must be some sort of electric field that pushes it this way. Okay? That could be generated by a positive charge over here. It could be generated by a negative charge over here. It could be generated by a crap load of charges hidden all over the page that just have a net force that points it this way. Okay? But the point about the field is you don't need to know where it comes from once you have it. If you know the force, you can predict the field. All right? So here are the options. Okay. So what we know is that without any of these charges, we know at this point in space, we have an electric field vector that points this way. And now we don't need any charges. All right? And we know if we put a positive charge here, it's still going to experience a force going this way. If we put a negative charge here, it'll probably experience a force going the other way. Okay? Which means this is the electric field at the location where the charge was. All right? So whether or not we know what charges caused it, and whether or not we know what charges are interacting with it, the electric field stands alone. Okay? It's all we need to determine what could happen if we put a charge there. And that way we can interchange the charges. We can do this for any charge. Once we know the electric field, we just throw the charge back in. Okay? So an electric field is measured in newtons per coulomb. So the amount of force you get per charge that you put in there. All right? And so, if you want to go back and forth between force and field, it's actually pretty straightforward. Okay? Really, the electric force is just the electric field times the... Oh, no. The electric field times the charge. Okay? So here's our electric field. Let's say we put a positive charge here, plus Q. Then this is plus QE. Then the force and the field are parallel. What if it's a negative charge? Minus QE. So the force and the field are antiparallel. And so it actually keeps the orientation based on the sign of the charge, but you only need one electric field. Okay? Well, then you're like, well, how do we get the field? But before we do that, let's try a problem. Okay? Let's try again. Interesting. All right. So, remember, when is force parallel to field?
When they're the same charge.
When the charge is positive or negative?
Positive.
Positive, right? For a positive charge, so if you ever want to know the direction of the electric field, it points in the direction that a tiny, tiny, tiny positive charge would move. Okay? So a positive charge would move this way. What is an electron?
Negative.
Negative. Which way is it going to go? The other way. Okay? So the sign matters. All right? That's going to be to the left. All right? All right. Let's try the next one. Better. Okay, so this is going to be B. And basically the way that this works, right? You want to figure out the way the electric field's pointing by figuring out where another positive charge would move. This one's stuck here, so it creates the field.
Oh.
Okay? If I put a positive charge here, which way does it move? This way. If I put a positive charge here, it's always moving away, right? So one here moves up, one here moves down. Okay? So this is what we want to do, right? If we're going to try to generate what the electric field looks like.
I think that's how like the fuse works.
So
Yeah, you'd have to add them.
here's our positive charge. All right, I'm going to draw little dots. You tell me which way the field points, all right? So if I put a dot here, which way does the field point? Up. All right, let's say I put a dot here.
To the right.
To the right. Let's say I put a dot here.
To the left.
Is it bigger or smaller than those arrows?
Smaller.
Smaller. Why? Further away. All right, if I put a dot here, down. Okay? If I put a dot here, smaller, out. Put one way over here. Right? Okay? So the way the electric field looks, if you have a point charge like this, something like this. And these are electric field vectors. Okay? And how do we know they're vectors? Well, they look like vectors because they're arrows. But you can see they're bigger as you're closer because this is the formula for the magnitude of the vector. So if R is smaller, F is bigger, or E is bigger. Okay, in this case. All right? What about a negative point charge?
Same thing but opposite.
Same thing, but they flip sign, okay? So a negative point charge, all the vectors are going to point in. All right, so this is the vector field. Remember we talked about how we're going to deal with vector fields. Bunch of little arrows in space, okay? These are the vector fields for just a single point charge, positive and negative. All right? And so how do we calculate electric field? We know that F is equal to Q times E. These are both vectors. Well, for a point charge, just for a point charge, what's F? How do we find the force from a point charge? It's the only equation we know. Coulomb's law, okay? It's the only equation we know from this class, all right? K Q1 Q2 over R squared. Well, let's say this is Q1. What do you think E looks like? Well, it's a lot like Coulomb's law, but what's it missing? Q1, okay? So the electric field, right, this is Coulomb's law. Here's our source charge. So we pull one out, right? The electric field looks like this. It's just Coulomb's law, and we lose a Q. All right? So this is called the source charge. This is the charge that generates the electric field. All right? The other charge is the charge that's in the field. So it's just you have to keep track of which one's which this time.
Wouldn't both charges just have their own electric field, though?
Yes.
So they're both simultaneously making their own field, but then also being acted on by everything else.
Yeah, but here, just like with this thing, right? We know there's forces on these.
Yeah, we just
And we know there's forces on these. But to calculate a particular thing, we don't need to calculate all the electric fields, right? We just need to decide which ones we care about. So yeah, every point charge has its own electric field. And it interacts with the electric fields of the other point charges. And we're going to do a whole lab on that in a couple weeks. So if you're really excited about looking at electric fields of point charges, then you are in luck. Okay? So this is the electric field for what? What?
Source.
One charge. 1 point charge. Okay? Which, you know, and once again, this is the distance between the centers. This is a constant. There's charge 1. Okay? So that feels fairly straightforward, but how often do you just have one charge? It's going to get weird. All right. Don't forget, still a vector. And what if we have 2 charges? What do we do then? Let's say we have an electric field generated by 2 charges, and we want to figure out the electric field at some point. What do we do?
Do it twice.
Do it twice. Add them together as vectors. Okay? So just like forces, you find the net electric field. Okay, so if you were okay with doing this, and whatever used to be over there, you're still okay to add electric fields. All right? So,
okay, so we're just calculating the electric field. It's sort of this Coulomb's law. And we have a charge located at the origin. We're just calculating the electric field at 2 points. So the nice thing about electric field versus electric force is we only have to deal with one charge, and then we're just dealing with the location of that location in space relative to that charge. That's where our R comes in. So to start out with, we'll just draw this out. So we have our charge at the origin, and that's going to be, we'll call this guy Q, which is -1 nanocoulomb. And then we have 3 different points that we care about, so I'll draw them with different colors. We'll start with this one. So this will be at, so this is at in centimeters. This is at 1 centimeter. So we have one here. We'll call point B. This is also at 1 centimeter. And it's point A. And then we also have one last point at point C, and that's at 1, 1. So here we have our 3 different points. And the key thing here is we're plugging into this equation. So we'll start out with point A. So the electric field at point A is going to be equal to KQ over the distance from R to A squared. And then this is a vector, so we have to deal with this vector like this, okay? So when we're drawing this out, this point at A, this is a negative charge, so that means that we have an electric field that points towards, if this were we want to think of our electric field at this point as a positive test charge, okay? So it would be attracted to the negative charge. So we know our electric field is going to point in towards the electric charge. So this is EA. So that's the direction that we're dealing with. We also know that our distance, which we'd call RA, is 1 centimeter, okay? So we plug in our values. Remember, K is just 9 times 10 to the 9th Newton meter squared over Coulomb squared. Our charge is the charge Q, which is 1 times 10 to the negative 9 coulombs. That's 1 nanocoulomb. And then our distance is 0.01 meters. Remember, it needs to be in meters, and we square that, okay? So 1 centimeter is 0.01 meters. The nanocoulomb, you'll notice we left off charge here. This is actually just the scalar quantity. When you plug everything in, that means you're going to get something like 90,000 newtons per coulomb, and that's going to be to the left. So we'll call that negative x hat, which is the same as to the left. Okay, so that's our first electric field value. So you could rewrite that as negative 90,000 newtons per coulomb x hat. And that would be a vector quantity for EA. If you want to do B, EB is going to be equal to KQ, same Q, over R B squared R hat. But if you just want to look at the direction this would be pointing, it's going to be about the same magnitude pointing down towards this charge. Remember, electric fields for negative charges point towards the charge. So this is going to be our EB. Remember, we're getting the magnitude from the equation. We're getting the direction from knowing how electric fields look. So once again, we have pretty much the same thing over here. All the values are the same. The only thing that's changed is the direction. So we'll change this color. And that means we have the same actual answer. So our answer over here should be the same. But the thing that's different in this case is that this is going to be in the negative y hat direction. And so that's our EB. Okay, so that's EB. And last but not least, EC has a slightly different direction, and if you want to look at where it's going to point towards your charge, but it should be a little bit smaller than EA and EB, because remember, our distance, right, which we'll call RC, should be equal to, well, let's see, we have a right triangle with two sides 1, so using the Pythagorean theorem, that's going to be the square root of 1 squared plus 1 squared, which is the square root of 2. So that's going to be the square root of 2 centimeters, okay? So when we solve for EC, we get KQ over RC squared in the R hat direction. So we get most of the same things. Just have to make this purple. But what's changed now is this is the square root of 2 times 10 to the negative 2 meters squared. And that's the square root of 2 centimeters, but remember, it's 0.01 meters, so you have to do the conversion from centimeters to meters. And this should be sort of at 45. Right, you can see this angle has to be 45 degrees. So you plug in the numbers and you get actually 45,000 newtons per coulomb, 45 degrees south of east, which we can just write as southeast. And that's your electric field for point C. So those are our 3 different electric fields for our 3 different points. You can see the charge stays the same for all of these. These are all just points in a total electric field, right? So if you wanted to draw the electric field for just a negative charge, you would have, have sort of big arrows, and as you get farther out, you'd get smaller arrows. And that's what the electric field looks like, but we're just calculating particular points relative to this thing. So not the whole field, just pieces of the field at a particular point. Okay, got a lot of these, a few other holdouts. Please discuss. Oh, nice. You guys are killing it. All right, we don't need to go over that. You guys just know everything. All right, okay, so remember, these are what the electric fields look like for point charges, okay? We also have these things called electric field lines. Now, those are a little bit more complicated. I mean, they look prettier and they're simpler to draw. So if you have a positive charge, the electric field lines look like this. Like this. And you have arrows on them. Okay, and you're going to say, well, we lost some information there because the vectors told us the magnitude. But you didn't, because if the lines are closer together, a couple rules for the lines. They start on positive charges. They end on negative charges. Okay? If the lines are closer together, you can assume the vectors are bigger. If the lines are farther apart, the vectors are smaller. So the density of the lines gives you the magnitude of the vector. The direction tangent to the lines gives you, density gives you magnitude, tangent to the lines gives you direction. So you get both things from the vector field that you can get, but they're easier to draw. Okay? And then you can imagine if you have a negative charge, the electric field lines go in. Okay, and the key is you always want them evenly spaced on the starting charge and evenly spaced on the ending charge. And it turns out if you have 2 things like this, right, the electric field lines connect. So you start on a positive charge. You can see these are pretty evenly spaced. They bow out and they end on a negative charge. And if you can see how the vectors work, right? The vector
here these lines are close together. You have a slightly bigger vector. It's tangent to the line in the direction of the arrow. Out here, you can see it's still tangent to the line, but it's smaller because the electric field lines are farther apart. Okay? So the electric field lines are a little bit easier to draw than the vector fields because you don't have to draw all these little points. But they tell you a lot about the vector fields. Okay? And, oh wait, I think I found a better one of these. There was like, maybe this is a good one. Yeah, there's good music too, so let's plug in the sound. So it turns out this is basically connected to a power supply. So the positive terminal is connected here, the negative terminal is connected here, and you put some little dye particles that have some like dielectric qualities, so they're like little polar molecules, and they spread out along the electric field lines. Okay, so these are the electric field lines for different configurations. So this would be like for a positive charge, right? You can see they all go out diverging in this nice pattern that's sort of a star pattern. And then this is for a plane. This is for a positive and a negative, right? Oh yeah, now they're going to tell you. The crystals are potassium permanganate. Pretend I knew that. Yeah, so you just put like some salt water. Why do you use salt water, by the way?
It's more conductive.
It's conductive, right? This is considered a dielectric, so it's a slightly conductive surface, and you put this potassium permanganate that is slightly polar, and it bleeds in the right direction of the lines. Okay? You can try this at home.
With adult supervision.
If you're watching yourself, technically, I think all of you guys are adults, right? All right. So that's what we got for today. I'll see you guys on Wednesday. We'll do some superposition, and we'll start integrating stuff. Are you guys excited? No?
I like calculus more than I like. Well, I like math, but it's easier for me.